Okay, so our progress so far is as follows. So let us have a quick review. We intend to define a measuring system on a non-empty set omega, right? We want to define a measuring system. It's a loose language I'm using. On a given non-empty set omega. What do you mean by measuring system? That is, we wish to associate with each element in a collection B of subsets of omega, a non-negative extended real number. So given a set omega, you want to define a collection of subsets of omega, a suitable collection. And for each of these elements in this collection, I want to have a non-negative extended real number. And this B should be rich enough and mu from B to R star, which is R union infinity. Satisfy certain axioms. Certain axioms. And what is the requirement of B and what is the requirement on mu are guided by our experience with standard measures like length, area, volume, and so on. Satisfy certain axioms guided by our experience with length, area, volume, etc. So this is what we were talking about. And this led to the abstract concept of sigma algebra and measure. So let us quickly recall those definitions. Definition. A sigma algebra, or let me put in slightly different way. You are supplied with a set B, a collection B of subsets of a set omega is said to be a sigma algebra in omega if B enjoys the following property. Basically, a sigma algebra is collection of subset of a given set omega, and that collection of subsets should have the following properties that we listed in the previous lecture. One is that null set is necessarily a element in that collection. Second one, if A is in that collection, then you should necessarily include its complement. A complement is in B, where A superscript C is the complement of A with respect to set omega. Complement of A with respect to omega. And third property that we would like to have in B is the following. If An belongs to B for all n in N, then union N belong to N, is in B. To put in simple language, B is closed under countable union. ANs can be disjoint or whatever it is. I don't bother. Whether it is disjoint or not, once you have a countable collection of elements in B, their union also should be in B. And you can see that with these three conditions, B will be closed under standard set theoretic operation. Like it will be closed under countable union by the very definition, countable intersection. You can combine 2 and 3 and use De Morgan's law. It is obviously closed under finite union and finite intersection. Once null set is there in B, due to 2, you can see that omega is in B. Therefore, null set and full set are in B, and so on. So, in short, B is closed under almost all set theoretic operations, countable number of times. Difference of two sets will be in B whenever two sets are in B, and so on. So this was the definition we made. To add to that and fix some terminology, let me write the following. If B is a sigma algebra in omega, have you done a course in topology or yet to do?
So we are doing.
You are doing, yeah. There also the basic setting is something like this. You have a set X and you have a collection of subsets of X satisfying certain properties. Yes or no? And what are those properties? Null set and full set are in tau, and tau is, and from where those axioms came? Those axioms came by studying properties of open sets in R or properties of open sets in metric space. Okay. So there also you have a collection, and collection satisfies certain properties, and that properties are guided by our own experience with open sets in R or open sets in a metric space. Are you with me? And try to compare. In topology, what are all the conditions? For sigma algebra, what are all the conditions? Try to compare. Okay. Anyway, if B is a sigma algebra in omega, then the pair omega comma B is called a measurable space. Is called a measurable space. If X is a set and tau is a topology on it, X tau pair is called a topological space. So always it is better to compare and contrast and study, so that, no, that's my view, called a measurable space. Okay. And the members of B the members of B are called measurable sets. Are called measurable sets in omega. If every subset of omega can be measured, then well and good, but we cannot expect it. Measurable space and measurable sets. These are two definitions that I am including along with what I defined previously. So, but the basic setting is sigma algebra. So that gives you what is the richness you want in B. Now the question is, what are all the axioms that you want in mu? And that leads to the following definition. This was made in the previous lecture as well, but let me repeat. Definition. I am going to define a measure. To be more precise, a positive measure. Later we can work with any measure, complex measures and so on. Okay, signed measure and so on. Okay. A positive measure, positive I will put in brackets, is a function mu defined on where? Where do you want to define measure? On B. And what is B in abstract setting? Sigma algebra, right? Mu defined on a sigma algebra B, that is mu is a function from B to R star, where R star I mean R union infinity. We allow it to be extended real number such that 1 mu of small usual B is greater than or equal to 0 for every B in sigma algebra B. 2 mu of null set should be equal to 0. And we already know that null set will be definitely an element in B. That is one requirement. If you take an empty bottle and measure its volume, volume of water is 0. If n belong to n is a disjoint countable collection. Disjoint countable collection of members of B then can you recall what's the condition you want on mu?
Mu of union of n
Mu of union n
equal
belonging to n should be is equal to summation mu of n belongs to n. And please bear in mind that this 3 is motivated from two principles. One is that the whole is equal to sum of disjoint parts, finite number of disjoint parts. And second one is method of exhaustion. We combined them and made this. Okay. Yeah. So this was made last lecture as well. Let me add one more terminology. A measure space, a measurable space I have already defined. Now it is measure space. A measure space is a measurable space. Measurable space means you have a set and a sigma algebra. Now, once you have a sigma algebra, you can talk about a measure. And if you have a measure as well, then you call it as a measure space. Okay, so let me put it in precise language. A measure space is a measurable space which has a positive measure. I will not add positive every time until I mention by measure I mean only positive measure defined on the sigma algebra of its measurable sets. Essentially, a measure space means you have a set, you have a sigma algebra, and you have a measure. So it is a triplet, omega, comma, b, comma, mu. That triplet is called a measure space. Okay. Let me give you some quick examples for this terminology. Let us consider an arbitrary non-empty set. Let omega be non-empty set. Take script b to be 2 power omega, the power set of omega. So definitely B satisfies all the requirement that we have put here. So B is a sigma algebra. Okay. So now I wanted to define a measure for each E in B. Define mu of E is equal to a well-known measure to you. Mu of E is infinity if E is an infinite subset of omega, and mu of E I would take as number of elements in E. If E is a finite subset of omega. By the notation mod E, I mean cardinality of E. Okay. And this measure is called counting measure. Okay. You can see that mu satisfy these three properties required. It is a good exercise to see. Okay. I will not write the detail. Note that mu is a positive measure. Commonly called counting measure. The terminology is justified because actually you are counting number of elements in E, called counting measure. Therefore, any set omega, you can have a sigma algebra, namely 2 power omega, and you have a measure mu, the counting measure. This is a measure space. Consequently, omega 2 power omega with mu as defined above is a measure space. Just verify that mu satisfy all the three conditions. Okay, two are trivial. Only thing that you have to verify is the third one, that is countable additivity. It is called countable additivity. Mu of disjoint union of countable sets is equal to sum of mu's of individual sets. This is called countable additivity. Okay. That is the only non-trivial thing to verify. Now let me give you one more example. Here, the underlying set I would take omega. I would take as an uncountable set. Let omega be an uncountable set. For instance, R. Okay. And let us take B to be the collection of subsets of omega as follows. Suppose B is the family of subsets A of omega where A is countable or omega minus A, that is A complement, is countable. The collection of all subsets which are countable or whose complement is countable. Okay. So here I am making two claims which you should verify. One is claim 1. B is a sigma algebra. B satisfy 3 requirements, of which only non-trivial thing is to prove that B is closed under countable union. And claim 2 is the following. I define a measure. Define mu from P to 0 infinity. I can say R union infinity and then I am putting a condition mu of E greater than or equal to 0. That is same as saying mu is from B to closed interval 0 infinity, infinity included. How do I define? Mu of B is 0 if B is countable. The element B belonging to script B is countable. And I will define it as 1 if B complement is countable. And that are the only two possibilities. By the very definition of script B, if I pick a B in B, either B will be countable or B complement will be countable. Okay. Define this. The claim is the following. Mu is a positive measure. Positive measure. So now you have a measure space. Omega, B, mu. This triplet becomes a measure space. Okay. So these two claims you can verify. It's just computations. It's a nice exercise. But before that, let me ask one thing. Here you have put a condition on the underlying set. Omega is an uncountable set. Why that condition? What happens if it is not uncountable? Let us say if it is countable, finite or denumerable. What happens?
Then B equals to power set of omega.
Yeah, B will be the power set, okay, which is not of interest. Already we have given an example by taking the entire power set as sigma algebra. So that we wanted to avoid, that's why. Otherwise, there is no much reason for why I am taking omega to be an uncountable set. I want to have a sigma algebra which is not entire power set. Okay. So this gives you two abstract notions, sigma algebra and measure, and a few examples. And this abstract setting we will be revisiting maybe at the fair end of the course. Okay. As I told you in the beginning, from now onwards, we wanted to study only about some special kind of sigma algebra and special kind of measures invented by Lebesgue. So Lebesgue measure, that's what we wanted to do. But since we were trying to give an intuitive idea of what is this measure and so on, I already given you the grand picture and final destination is sigma algebra and measure. Okay. Now we are going to take a, I should not say detour, but anyway, now what we are going to do is to discuss some special types of measure, especially a measure on the real line. Okay, and that is called the Lebesgue measure. But before doing that, well, you wanted to define or generalize length, area, volume, and you went all the way up to sigma algebra, measure, measurable space, measure space, and so on. One thing still I have not answered is why one want to do all these things. Why do you want to generalize? Okay. As I told several times, the idea comes from integration. Okay. Why one want to measure things other than intervals in R? If, if you want to answer it, I have to seek help from integration theory. So our next purpose is to see why this generalization. Again, not very mathematically, an intuitive idea I will give. Then I will start Lebesgue measure. Okay. So the question that I want to answer now is why we want to generalize the concept of length, area, volume, etc. and study about measure. The generalized concept is called measure. Okay. So let us try to answer this in an intuitive manner. Okay, so let us try to review our idea of integration, an overview. Okay. So I think most of us, at least in the beginning, had a common misconception that integration is antiderivative. Yes or no? At least in the beginning. Maybe now you are not having that misconception. You know what integration is, I suppose. But in the beginning, we always thought integration is something like an opposite process of differentiation. Right? So let me tell you that it is not correct. It is a misconception. So that is the first deep rooted thing that you should have. Integration is not antiderivative. For instance, suppose you are asked, suppose we are asked, I should say, to compute integral, let us say 1 to 2 x square dx. What we will do? We will find one function whose derivative is x square. That function is called antiderivative of x square. There may be several functions. One such function we know is x cubed by 3. So let us take that antiderivative and then we will compute it at 2 and compute it at 1 and find the difference. Okay. So if I am making some mistake, you can say 8 by 3 minus 1 by 3. I suppose this is 7 by 3. Right? Well, if you are asked just to compute integral 1 to 2 x square dx, this is very well accepted and this is a correct procedure. What is wrong is to think that conceptually integral 1 to x 2 x square dx is same as antiderivative. I am not saying the process is wrong. What is wrong is conceptually integration is not antiderivative. Okay. For instance, you can say all these things in some special case. Suppose f of x has antiderivative capital F of x, that is capital F dash x coincides with small f x, and suppose further that f is continuous. F of x is continuous on AB. Then integral a to b fx dx will coincide with capital FB minus capital FA. But integral a to b fx dx has a different meaning. Whatever be that conceptual meaning is, it will finally coincide with FB minus FA. That too with some additional assumptions like small f of x has an antiderivative and small f of x is continuous and so on. And who tells you that these two are equal?
Fundamental theorem of calculus.
That is
Fundamental
fundamental theorem of calculus, right? Fundamental theorem of calculus. So it is the fundamental theorem of calculus who tells you that the integration concept coincides with antiderivative evaluating at the endpoints. But integration has its own meaning. Okay? One of my favorite author in many different branches of mathematics, he has written books, is K.D. Joshi. He has a nice book on topology as well. Okay, so you can refer it. Generally, people hesitate to give Indian authors book. I don't know what is the reason behind it, but there are several good books written by Indian authors as well. And K.D. Joshi is one of my favorite author and also a speaker. I had chances of hearing him, and he has written in his calculus book that this integration and antiderivative are two different things, though we have a misconception and computation is true. What you can compare is like this. Integration and antiderivative may not be may not be the same object, but it is two different person, okay, brought up in two different territory. And finally, one person comes and identifies that, hey, people, you two are twins. And that person is fundamental theorem of calculus. Otherwise, they have their own existence in a different world. They are not same. Are you with me? So it is not like a person with beard and without beard. No. One place you are putting 1 and 2, and antiderivative means you will just put integral x square dx. So it is not like same person with beard and without beard. It's not like that. It is a two different people brought up in two different places, and ultimately one person comes at the end. In the climax, one person arrives and tells that you two people are connected. And that person who identifies the connection is fundamental theorem of calculus. And he compares it with old Hindi movies where there will be two twins born at same place but separated because of some reason, and finally in climax somebody comes and tells you and identifies that these two people are twins with some evidence. Okay, so like that, fundamental theorem identifies these two are same. But that's not what I wanted to say. By this, you should able to understand that integration is not my comments, and my so far what I wanted to say is only that integration is not antiderivative. Having said it is not antiderivative, next thing is to say then what it is. What is integration then? Okay, there comes, as you know, the idea of who gave a formal definition for integration? Rayman. So there comes the Rayman theory of integration. Rayman tells you that this is what integration is. Integration can be thought of as area under the curve in some situation and so on. Okay. So the first and foremost formal definition of integration was given by Riemann. First formal definition of integration is given by Riemann, as you all know. So let us try to give an overview of Riemann integration again intuitively. And let us see why Riemann is not enough, why people have extended it. There comes the idea of measure. Okay. Now again, let me go back. I told you that integration is not antiderivative, and K.D. Joshi compares it with, two concepts, limit extending to C f of x and f of c. Limit extending to C f of x and f of c. They are equal, but not always, under certain conditions, right? What is that condition?
Continuity.
Continuity.
F is
So if you know a priori that f is continuous at C, then limit extending to C fx coincide with fc. But in general, limit concept is different from value of the function at the point. Yes or no? Now, how he let me just share thinking that you will also enjoy. How he tried to explain this is like this. Suppose you have a colony in which there were several houses. Okay, so X's are houses, and F, the function what you do is you are trying to get the income of owner of that house. So f of x measures income of owner of a particular house. So limit extending to C f of x is like, what is the impression you get about income of owner of the house C from the income of neighboring houses, owner of the neighboring houses? Are you with me? I don't know whether I'm wasting time, but it's okay. So let me take 5 minutes. Let me repeat. X's are like houses and f of x's are like, it measures the what is the income of the owner of that particular house. So what is limit extending to C f of x? It is the assumption or the impression that you get about income of the owner of house C by knowing the income of the neighboring houses. Okay, that is limit extending to C f of x. But that may not coincide with f of c. For instance, you measured the income of neighboring houses and you got some conjecture. But you went to the Cth house. Cth house may not have an owner at all. Even if there is an owner, he may be very poor. He might have somehow landed in that colony because of some reason. So the impression that you get about income of owner of the Cth house may be entirely different from what actually is the owner of the Cth house. There may not be an owner. Even if there is an owner, his income may be far different from what is the neighboring income. Are you with me? So this is how he compares. Okay, like this, whenever he introduces some concept, he compares it with some daily day-to-day life and try to make us understand this is what it is happening. In that way, K.D. Joshi book I always enjoy, but unfortunately he doesn't have a book in measure theory. In topology he has, in calculus he has. Okay. So let us go further. So I was telling that integration is not antiderivative, and the first man who came with a satisfactory explanation for what is integration is Riemann. And again, if you see at the core, Riemann's idea is just a common sense. It is just a common sense. Okay. What is that common sense? Rayman has put in a nice mathematical language. The question that we are asking is the following. Suppose you have a wire, let us say, of varying density. The density varies with the place. So f of x is the density at xth position. What is the mass of that wire? That's the question that we want to answer. Okay, you have a wire of varying density. Fx measures the density at Tx. The question is, what is the mass of that wire? This is the question Rayman wanted to ask. So what Rayman did was, instead of working with an arbitrary wire, he took a special case. Let us take a wire which is of nice shape, that is uniform density. You consider the function is constant. Put it in max language, consider the function to be constant. F of x is equal to c for all x in AB. The density is same. You have a wire of uniform density. Okay. Now I want to find the mass. And what is the mass of this? He defined integral f of x dx as c times. So suppose this is A, this is B, the function is C. What is the area under the curve? Yes, it is a rectangle, right?
CB minus A.
C
CB
times
minus A.
B minus A.
B
That
minus
is
C.
C times, if you call this AB as I, the interval I, then C times length of I. Okay, so integral A to B fx dx in the special case when fx is a constant is C times B minus A. Okay, now I have written it as C times L of I. You can observe that measure slowly creep into picture. When you have interval, length is the measure, standard measure. So while defining integration, knowingly or unknowingly, measure comes into picture. Okay. Now what Rayman did was, instead of this simple wire, let us say the wire can be cut into several pieces of uniform density. That is, instead of this, he considered piecewise function or step function. He considered the step function, something like this. So total interval is AB. That AB can be subdivided and into finite number of parts. And in those parts, fx has constant density. Okay. So let us say this is some point x1. This is some point x2. And this is x3 and so on. Okay. So now you want to find the mass of this wire, or geometrically area under the curve. What you will do? Suppose this piece is constant density C1. This piece has constant density C2. This piece has C3 and this has C4. Okay. Then what will be area under this curve? C1 times L of I1 plus C2 times L of I2 and so on. Sigma I equal to 1 to 4 Ci L of II. By II, I mean these intervals. Are you with me? Do you follow?
Yes, sir.
Again, you can see that the length comes, measure comes. Okay. So from the very base level, he went to slightly complicated thing. Now, this is the underlying idea. Now, if you have any arbitrary function, let us say, you try to do the same thing. That is, divide this interval into several subintervals. X1, X2, so on. Finite number of subintervals. x0, x1, x1, x2, and so on, xn minus 1, xn. And in each of these subinterval, let me write it as xi minus 1, xi. A typical ith subinterval is this. If you vary x over xi minus 1, xi, definitely the function value will vary, fx will vary. But you approximate this function with a constant value. Okay. Instead of considering that the function varies when x varies over xi minus 1 xi, you assume that the function behaves like a constant throughout xi minus 1 xi. So this is that constant, suppose. And then it is something like what you have previously done, piecewise function or step function. And approximate the area under the curve f of x from xi minus 1 to xi with this area under the rectangle. This is what Riemann did. Yes or no? I am not talking in a formal language that we will do soon, but this is the underlying principle. Divide into subinterval, and in each subinterval, you don't consider the function to be varying. You consider that the function is a constant, so that in you will be having a step function like. Okay. And area under the actual curve f of x, you approximate by area under this constant, which coincides with our base case, c times L of I. This is only an approximation. Of course, our next job is to make this approximation better and better. Okay, that's what Riemann did rigorously. Okay. So that we will do. We will recall those definitions and so on shortly. But though this gives you two things. One is that a formal definition for integration. And second one, as you all expect, integration A to B fx dx is attached with area. That is not revealed if you use fb minus fa idea. How integration is attached with the area is not clear if you do just FB minus FA. Riemann is the person who gave that this integration has a precise formal definition, and that formal definition enabled one to attach integration with area finding process. So far, so good.
Yes, sir.
This is the good news about Riemann's integration theory. Formal we will discuss later. This is the good news. But the bad news is that there are several deficiencies in Riemann's integration. Let us not worry about what are all those deficiencies. We will see soon what is Riemann's formal definition, what are all the deficiencies you will see soon. But for the time being, you understand that there are some, or you accept that there are some deficiency, even though Riemann gives a formal definition. And those deficiency motivated Lebesgue to look into integration theory more rigorously. Okay, so Riemann's integration, let me just put these things here. Riemann's integration, formal definition it gives, and it connects integration with summation and area finding. Summation and finding area. By the way, have you ever thought why this integration sign is like this? Again,
Yes,
it
sir.
comes from summation.
Summation.
Yeah, not exactly summation, summa, Latin word, which means summation. So that S is being used. You can see in the base level, what you are doing is just summation in the continuous scale. C you are multiplying with B minus A. It is like summing C for all values between A and B, right? Multiplication is a summation. Yeah. Anyway, so Riemann gave this, but however, Riemann's integral has some deficiency. Let us accept that statement. We will see what are all the deficiency we are talking about. Has some deficiencies. Okay. And Lebesgue came with more general, satisfactory definition and explanation for integration. Again, of course, the course is about Lebesgue measure and Lebesgue integration. But before that, let us try to understand what Lebesgue did. Again, intuitively, let us try to understand. What Lebesgue did is, he revisited Riemann's process and tried to interpret in layman's language. Okay, let me try to give you this example. Now, you consider this f of x, that curve, as you have packed several currency notes, let us say. So there are several currency notes of different dominations. What is that word exactly used? If you have, say, I think you understood what I am saying. There are some 500 rupees note, there are some 100 rupees note, and so on. Okay, they are neatly packed, let us say. Okay, now you want to find the total amount available in that whole bundle. Okay, what Riemann did was the total bundle he divided into several sub bundles. Okay, and each sub bundle there may be currency notes of different values. 500 rupees note may be there, 100 rupees note may be there, 2000 rupees notes may be there. But what Riemann did was forget about this varying notes and approximate it with the same note, right? Instead of considering fx to be varying, consider it as a constant, and that constant he multiplied with number of notes. Are you with me? The total bundle of notes divided into several sub bundle. Each sub bundle, the notes are of different value, but Riemann approximated with a single representative and multiplied that value with number of notes in that sub bundle. That's what Riemann did. But this is not the way to count currency, right? What is the correct way to do currency?
We will bundle them according to the.
So yeah, sort it out according to their value, right? So you stack all those notes with the 500 value, and then all those with 1000, all those with 2000, and so on, and then multiply it with number of notes. Number of notes. So you have to sort out so that the notes are having the same value. That means instead of dividing the domain, you have to divide the values, right? That means you have to divide the range. You have to divide the range and look at those part where fx has the same value, right? And then come to the domain. I will explain this with a simple example and then count. And this is Lebesgue idea of integration. Let me explain through a simple example. Okay. Suppose f of x is like this. Most easiest thing is to work with the step function. Okay. So you have, let us say, 0, 1 interval, and at some place fx takes value alpha 1, some place it takes alpha 2, Some place it takes alpha 3 and so on. Okay. This is I1, interval I1, and this is I2, subinterval I2. This is I3, and this is I4. Okay. So if you want to find area under this curve by Raymond's method, okay, suppose f of x takes 4 values, alpha 1, alpha 2, alpha 3, alpha 4, respectively in I1, I2, I3, I4 over interval 0, 1. Suppose. Then by Raymond's method or a common sense, integral 0 to 1 f of x dx is equal to alpha 1 times length of I1 plus alpha 2 times length of I2 and so on. Summation I is equal to 1 to 4. This is Raymond's idea. What Lebesgue told is that instead of dividing the intervals over the x-axis, you look at the values. Okay. So what are all the four here in this example? Fx takes only 4 values. What are those? Alpha 1, alpha 2, alpha 3, alpha 4. So we segregate so that the nodes are of same value. Alpha 1, that is one bundle. Alpha 2, alpha 3, alpha 4. So we have 4 bundles. Now what we do is look at those nodes. So you consider F inverse of alpha 1. That will give you what are all the places where the function takes value alpha 1, right? And consider F inverse of alpha 2. Okay. So what you do is consider this F inverse of alpha I. In this case, they are intervals. What is F inverse of alpha 1? Where the function takes alpha 1 value. It is I1. It is I1 in this case. Okay. So what Lebesgue did is Lebesgue. He defined integral 0 to 1 fx dx as summation alpha I. Okay. The function values times where that function takes the value f inverse alpha I, and you want the length of this. Modulus of f inverse of alpha I. In this particular case, it will coincide with length of II. Are you with me? This is length of II in this particular case. But the inherent idea is don't divide the domain, divide the range and consider what are all the different values of the function and multiply it with the size of the sets where that function assumes those values. I repeat, multiply the function values with size of the sets where the function takes that value and sum it up. Are you with me?
Yes, sir.
Multiply function values with sizes of the sets where the function takes that values and do it for each values and sum it up. But do you see one issue here? In this case, okay, F inverse of alpha I coincided with intervals, and you can talk about length of interval. Okay, and this here in this example, size of f inverse of alpha I have already written that is length of IA. But instead of this step function, suppose you have a general function and try to do this. Means you collect those where fx takes same value and then consider its inverse image, f inverse of that. Can you expect f inverse of that will be always an interval?
No, sir.
You cannot
sir.
expect. So I want measure for that set. Are you with me? So instead of length, now I want measure for f inverse of alpha I. This is the reason Lebesgue wanted something apart from intervals and lengths. So I want size of these inverse images. And if I want the size of inverse image, keep in mind that inverse image may not be always intervals. It can be an arbitrary subset of R. And for an arbitrary subset of R, I can't talk about length. I need a suitable generalization for length. And that led Lebesgue to define measure. And once he has measure, he could define integration. How did he define integration? Integral of fx dx is equal to summation of all distinct values of function times sizes of the sets over which those values are assumed. Is it clear? Summation of all distinct values of the function times sizes of the sets over which those function values are assumed. That is sizes of f inverse of alpha i's for distinct alpha I. This was the Lebesgue idea. Is intuitively it is clear or what?
Yes, sir.
So what's the difference? Now tell me, what's the difference between Riemann and Lebesgue? It is same. Essentially, both wanted to find total value of money. But Lebesgue divided the total bundle into several sub-bundles, and each sub-bundle was approximated by a constant value. Okay. But Lebesgue did it in a more common sense and intuitive way. Instead of just like that subdividing the bundle, he divided the sub-bundles according to the value of the function. Yes or no? And then multiply that value with number of nodes in that bundle. That's what Lebesgue did. Okay. So instead of dividing the domain, he divided the range. And look into f inverse of distinct values of the function. And unfortunately, this raises the question. If I want f inverse of distinct value, that f inverse can be arbitrary sets. And I want some means to measure these sets other than intervals. And further, suppose it is like this, then the Lebesgue integration will coincide with
Length of interval.
Riemann integration, because the size of f inverse of alpha I will coincide with the length of II. So it is not just like that he is defining something. Whatever Riemann can do, I can also do, and I will get the same value, right? And there are certain deficiencies of Riemann. Riemann cannot integrate certain function, and those function I can integrate. So Lebesgue came up with a more general one. Okay. And in that process, he naturally needed measure of subsets of R, not just measure for intervals. He want measure for subsets of R. This is how integration and measure is connected. Okay. So I hope that this simple example gives you the idea that length comes into the picture when you are talking about integration. But when Riemann did, length was sufficient. However, Lebesgue wanted to overcome the deficiency of Riemann integration, and doing so, he understood that length is not sufficient, but we want a more general concept, and that's how he introduced the measure. Is that clear? Is it make sense? Now revisit the title, measure and integration. You understood there is some connection. Integration process automatically needs measure. Okay. So having said this, what do you think? what we will do next. Why all these things? Why you wanted measure? Because you wanted integration, Lebesgue integration. Why you wanted Lebesgue integration? Because there is deficiency in Riemann integration. So what should be the best starting point now?
Connecting measure and integration.
No, what are all the deficiency of Riemann
Riemann
integration?
integration.
What are all the deficiency of Riemann integration? No, then define Lebesgue and then say that by Lebesgue these deficiency can overcome. So what I am going to do next is to recall Riemann integration, tell you mainly what are all the deficiency we are talking about, and then start with Lebesgue measure. So before Lebesgue measure, I have again things to do, that is Riemann integration and its deficiencies. Okay. So next target is this. Riemann integration and some of its deficiency. So quickly let us recall our progress so far is that measure is a more generalized concept than length, area, volume, and so on. And in the process of doing so, we needed the abstract idea of sigma algebra and measure. And those things we will revisit at the end of the course. Next, I wanted to give some special type of measures introduced by Lebesgue. And the purpose of introducing that measure was Lebesgue integration. And the purpose of introducing Lebesgue integration was to overcome the difficulties of Riemann integration. And intuitively, I have already told how Lebesgue measure is, measure and integrations are connected, and why one want to generalize to measure, not stop with the length. Those things I already told. Okay. Now, I think it will be better to start with Riemann integration and talk about its deficiency and then go to Lebesgue measures. Okay, so I will be quick here because you might have already studied what is Riemann integration. The idea is simple. Divide the total interval into subintervals, and in each subinterval, assume that function takes a constant value, so that you can talk about rectangles instead of arbitrary shapes, and approximate the area of the arbitrary shapes with rectangles. Okay, area of the rectangles. That's the idea. So let me start with definition. Definition of what? A partition. As I told you, I will be very quick here, but I want to record all these terminologies. Suppose, by the way, have you studied Riemann integration as a part of real analysis course or not? Before
No,
that
sir.
in BSc?
No, sir.
Maybe in BSc you have studied, but not as a part of your M.sc course, right?
Yes.
Yeah. So it is worth to record. Suppose A comma B are two real numbers with A less than B. Now I can talk about the closed interval AB. A partition of closed interval AB is a finite list of points. That's it. Finite list of points or a finite collection of points. Okay. X0, X1, X2, and so on, Xn. But there is some condition of the form. First of all, X0 should coincide with A. X0 is equal to A. The last one, Xn, should coincide with B. and it should be strictly increasing. Less than x1, less than x2, and so on. Less than xi minus 1, less than xi, so on, less than xi. Okay. Any finite list of this is called a partition. Okay. Note what partition does. Once you fix a partition, the total interval you can write as union of subintervals. Okay. We use a partition of AB to think AB as union. AB as union of closed subintervals. Total bundle of nodes you want to treat as union of subbundles. AB is equal to x0 x1 union x1 x2 union etc. union xn minus 1 xn. This is trivial. Once you have a partition, you can see. Now let us try to give a neat. I told you that what Riemann did was in each of the subinterval, instead of considering fx, original fx, consider fx to be a constant, so that you can talk about area of the rectangle. Okay. What constant I should consider? Fx is equal to some c, which could be the optimal c to consider. Okay. For that, he introduced certain notation, clean notation, supremum, infimum, and so on. Okay. So next, let us introduce. Next, let us introduce some notation. A clean notation for supremum and infimum of a function over a set. If f is a function from a subset of R to R, then infimum of f over a is defined as infimum of f of x when x varies over a. Infimum of the range set. I will write as inf f. And sup f, this is just for notation, is supremum of f of x, x element of a. I don't claim infimum and supremum exist as a finite real number. I don't claim, because there is no condition I have imposed on f. Okay. It can be a finite real number, or it can be infinity, minus infinity, whatever it is. Okay. Now, next definition. These are all for equipping ourselves to define Riemann integral. Suppose f from AB to R is a function and P is a partition of AB. P is a partition of AB. What is a partition? I already told. That is a finite list of elements. Say P is x0, x1, x2, so on, xn. Okay, this is the partition I am fixing. Then lower Riemann sum. Lower Riemann sum. The notation I am putting is L, F, P, AB. And upper Riemann sum I will denote it as U, F, P, AB are defined as follows. Are defined as follows. lower Riemann sum LFPAB is equal to, what you do is you partition. Once you partition, you will get subintervals. Okay. And each of the subinterval, you want to approximate the function by a constant. And which constant I would take? You take, instead of f of x, x varies over xj minus 1 xj. You consider f of x to be same constant, and that same constant is infimum. Then you will get lower Riemann sum. The constant you take it as supremum, then you will get upper Riemann sum. Okay. So LFPAB is summation j is equal to 1 to n inf f over xj minus 1 xj, that interval, into length xj minus xj minus 1. This is lower Riemann sum, and upper Riemann sum is UFPAB. Similarly, consider each subinterval. In each subinterval, instead of considering f of x, consider a constant. What is that constant? Sup f over the interval. And multiply it with the length of the subinterval. And do it for each subinterval and sum it. Okay. So what this gives, if you think geometrically, this is your function, and this is xj minus 1 xj. Okay. And this is your xj minus 1 xj. And infimum of those, when x varies over this, infimum is this one. Okay. But you approximate the whole function by that same constant. Okay. So this is what you are doing for LFPAB. And for UF, what you are doing is take xj minus 1 xj. F is varying. Over that, the highest value of f, in roughly, that is supremum actually, is this value. And you take that to be same everywhere. So this LFPAB and UFPAB approximate area under the curve, right? If the function is non-negative, you can say that it is an approximation of area under the curve. Okay. And what is now induction? If I consider the lower Riemann sum, the lower Riemann sum is always less than the area under the curve. Intuitively, right? And upper Riemann sum is
more than
the
area under the
area under the curve. Okay. Now what you do is, instead of working with a particular partition, you take a partition and refine it. When I say refine it, you take more points, add some more points. So P is this, I consider P dash, and P dash is obtained from P by just adding some points. Okay. And then you compare what happens to lower Riemann sum and upper Riemann sum. So basically we are trying to compare lower and upper Riemann sum when partition changes. Okay. And that is given by the next theorem. I will not prove these theorems. Basically, we want to compare lower Riemann sum corresponding to different partition and upper Riemann sum corresponding to different partition. Before that, for same partition, it should be clear that lower Riemann sum is less than or equal to upper Riemann sum. It is very clear, right? Suppose f from AB to R is bounded. I assume bounded so that I can guarantee this sup, inf, etc. are finite. Okay. Suppose f from AB to R is bounded and P comma P dash are two partitions of AB. Now, what is the connection between P and P dash? Such that the list defining P, partition means there is a list of points. List defining P is a sublist of list defining P dash. The points in P are there in P dash and P dash has more points possibly. Then lower Riemann sum of F corresponding to the partition P on the interval AB is less than or equal to lower Riemann sum corresponding to F corresponding to partition P dash in the interval AB. So lower Riemann sum increases when partition becomes better and better, finer and finer. Points are more and more. And as you know, L is always less than or equal to U corresponding to same partition. UF P dash AB. But when you compare upper Riemann sum corresponding to two partition, upper Riemann sum corresponding to finer partition, partition with more points will be less than or equal to upper Riemann sum corresponding to the original partition. Put in loose language, lower Riemann sum increases and upper Riemann sum decreases as partition become finer. Refinement we say. Refinement in the sense a partition will be called, P dash will be called as refinement of P if P dash include all points in P, possibly something more. Okay, so this theorem you can try to prove. Another result concerning the upper and lower Riemann sum is the following. Yeah, let F from AB to R be a bounded function. Boundedness is a blanket assumption here because then you can guarantee supremum and infimum to be finite. Be a bounded function and P comma P dash are partitions of AB. I don't consider any conditions on P and P dash. They are just two partitions. I don't say P dash is a refinement of P or something like that. Okay. Then lower Riemann sum corresponding to P is less than or equal to upper Riemann sum corresponding to P dash. This is not that trivial as you think. For a fixed partition, it is trivial that lower Riemann sum is less than or equal to upper Riemann sum corresponding to same partition. But here we are comparing lower Riemann sum corresponding to one partition with upper Riemann sum corresponding to any partition. Okay, so lower Riemann sum corresponding to any partition will be less than or equal to upper Riemann sum corresponding to any partition. P dash can be P, P dash can be anything else. It may not be a refinement. Okay, so this is a stronger result. Please understand. Now definition. By the way, if you see the geometrically what is happening, lower Riemann sum, upper Riemann sum, etc. are for approximating area under the curve. Lower Riemann sum try to approximate the area under the curve by rectangles of lesser areas than the original. So it is something like approximating from inside. And upper Riemann sum try to approximate the area by rectangles of more areas. So it is something like approximating from above. One is from below and one is from above. Okay. Keep that in mind. Suppose f from AB to R be a bounded function. Is a bounded function. The lower Riemann integral. The lower Riemann integral the notation I used is this. Integral a to b f dx with a bar lower. Okay. Is defined as lower Riemann integral of f dx is equal to, you consider lower Riemann sums p a b. Okay. So now you should guess. Now I can change partition. And you are finding or trying to approximate area under the curve by lesser areas. Right? Areas of rectangles with area lesser than the original. So what I should do?
Supremum.
I should take supremum over all partition. Sup over p. So that intuitively it is clear that the lower Riemann sum become better and better. Okay. And upper Riemann integral is defined as upper Riemann integral. URI I will write. Notation is this: integral a to b f dx with a bar upside is defined as integral a to b f dx upper Riemann sum is equal to u f p a b. Find upper Riemann sum. That means you approximate area under the curve by area of rectangles from above and then make lesser and lesser. Okay, so that is infimum. Infimum over all partition. Where infimum and supremum is taken over all possible partition. That I should explicitly say. Now you can understand we are taking supremum of lower Riemann sums because adjoining more points increases the lower sum, that we have proved. If you adjoin more and more points, it will increase the lower Riemann sum. That's why we are taking the upper bound, least upper bound, and adjoining more and more points, refining the partition. The upper Riemann sum will decrease, go on decreasing, and so you take infimum. Okay. So, and we prove and we expect that if you take supremum, it gives more accurate estimate of area under the curve. Okay. Now a theorem. You have already seen the connection between lower Riemann sum and upper Riemann sum corresponding to any partition. LFP and UFP dash. Keeping that in mind, can you compare lower integral and upper integral? Suppose that's the next theorem. Suppose f from, give me 2 more minutes, I'm stopping now. Suppose f from AB to R is a bounded function. Can you guess what will be the connection between lower Riemann integral and upper Riemann integral?
Less than equal to.
Lower Riemann integral, yeah, is always less than or equal to upper Riemann integral. That will follow from the previous theorems that we proved. If you see, the lower Riemann integral and upper Riemann integral can both be reasonably considered as area under the curve. Okay, approximation I'm saying. It's a good estimate. Now question is, which one I will use? Whether I will use lower Riemann integral as a best estimate, better estimate, or the upper Riemann. One is approximation from below and one is approximation from above. One is like inscribing and one is like subscribing. Okay, which one I should use? Instead of dwelling on this problem, what Riemann did is, if they are equal, he called it as integrable. And he worried only about those functions for which lower integral and upper integral coincides. So that's the last point that I want to choose. I want to make today. So I repeat, both this lower and upper Riemann integral seems to be a reasonably good approximate for area under the curve. But instead of deciding which one we should choose, what Riemann did is he considered only those functions for which both coincides. Okay. So let me make the definition. A bounded function on a closed bounded interval is called a bounded function f on a closed bounded interval AB is called Riemann integrable. Riemann integrable if lower Riemann integral A to B f dx coincides with upper Riemann integral f dx. And in that case, if f is Riemann integrable, then Riemann integral of f denoted by integral A to B f dx is defined as any one of them. Because anyway, we are considering only those functions for which both coincide, is defined as integral A to B f dx is equal to integral A to B f dx, lower Riemann integral or upper Riemann integral. So we have defined Riemann integrability. So I will stop with this. Now we will see some nice properties of Riemann, but more than nice property, what we are interested is in. Can you tell me? Just for my satisfaction. What we are interested is, what are all the deficiencies? Okay, because that is the motivating factor for Lebesgue to come up with his idea. Thank you.
Thank you, sir.